The fundamental theorem of algebra. What this states is that if f of x is a polynomial of some degree, we'll use the letter n to represent that it could be any number. It could be degree of 1, 2, 3, 4, something like that, as long as n is greater than 0. So that means it's not 0, nor is it any negative values. Then your function f should have at least 1, 0. And remember, our zeros are our x-intercepts, anywhere it crosses the x-axis, right? So, in the box here, we'll write our little theorem. If our n is greater than 0, then we will have at least 1, 0. And then they give us a few examples. So in this first picture, we can see that's our linear function, right? And it says this is the function f of x. It would have an exponent of understood 1 there, right? 1 is greater than 0. And you can see, if we were to draw a line on here, here's my x-axis, we do in fact end up having at least 1, 0, right? Okay, for this next function, my exponent is 2. This is our quadratic function, x squared. And 2 is greater than 0. We do, in fact, have at least 1, 0, right? For that next function, we've got x cubed minus 4x squared plus x plus 6. Remember, the degree of your function is the highest degree there, right? So the degree of this function is 3. And we do happen to have at least 1, 0, right? Because that 3 is greater than 1. So all this theorem is saying is if your highest exponent, your degree of your function, is greater than 0, so a positive number, then you're going to have at least 1, 0 in your function. Okay? Speaking of if it has to be greater than 0, let's also talk about what happens if it is 0. So if n does equal 0, you might not have a 0. Okay, so here they give us the function 2x raised to the 0 power. Well, we know anything raised to the 0 power becomes what? 1. So this is equivalent to 2 times 1, right? And 2 times 1 is just 2. So that's why in this picture you can see that we have a horizontal line here at 2. So this is a prime example. My exponent was 0, and did we ever touch the x-axis? So no zeros here. All right, so if it's greater than 0, we'll have at least 1. If it is 0, we might not have any at all. Okay, we also have what's called the linear factorization theorem. And this says if your polynomial of degree n, as long as that n is greater than 0, so like what we talked about for the first theorem, then f has precisely n linear factors, and therefore precisely n zeros in the complex number system. So here they're saying not only will we have at least 1, but like these pictures showed, your degree should match the number of zeros that you have. So like our exponent or our degree here was 1, and we had 1 0. Our degree here was 2, and we had 2 zeros. Our degree here was 3, and we had 3 zeros. Okay? So down here, in this picture that they give us, they ask what is the degree of this function? 3, right? Our biggest exponent is 3. So that should tell us we're going to have how many factors? 3, right? Remember, your factors are what they look like before they become the zeros, right? When it's in the parentheses. So if we've got a degree of 3, we should have 3 zeros. Okay? So 3 factors means 3 zeros. The catch here is that they may not all actually touch the x-axis, because remember, sometimes things are not able to be factored, right? Doesn't mean that they don't have some value, right? But sometimes we use quadratic formula to find them. And then what could happen is maybe not only do we get a decimal, but when we're using quadratic formula, we end up with a negative under that square root. We can't take the square root of a negative number because those are imaginary numbers, right? So we are going to have 3 zeros, but those 3 zeros could be imaginary, or they could be real. We won't know until we go and find them. All right. Then we have what is called the remainder theorem. This says when the polynomial p of x is divided by x minus a is just any factor. If that is a factor of your function, then our remainder should end up being 0, right? It should go in nice and neat and evenly. All right, so let's say that we had the function x squared minus 5x plus 9, and we are told to divide it by x minus 1. So basically we're checking to see is x minus 1 a factor or not. So what we could do is what we talked about last week, right? We can just use synthetic division. So what would I put in the box here? 1. And then all my coefficients, right? 1, -5, and 9. All right, what do you guys think? Is it a factor? No, why not? Because it had a remainder. Good. Okay, so that's one way we can check by doing synthetic division, like we had talked about last week. Another way you can check is by simply taking your value and substituting it into the equation. So like you guys said, x minus 1 is actually the value of positive 1, right? So what I could do is just go and plug 1 in for all the x's. So I could have 1 squared minus 5 times 1 plus 9. Okay, so then this would be 1 minus 5 plus 9, right? And 1 minus 5 would give us -4, right? 1 minus 5 is -4 plus 9. And what is -4 plus 9? 5. So that is like your remainder. So if you don't get 0, then you know that it didn't work. So either way is a fine way to check it, whatever you prefer to do. All right. Okay, flip it over onto the next page. Okay, you're going to do the same thing that we just did for this example on example 1 here. It says find the remainder when f of x is 4x to the third minus x squared plus 2x minus 5 is divided by the factor x plus 2. Basically, they say you're checking to see is x plus 2 a factor. Okay, so I want you to try it using both methods. First, do synthetic division, and then plug in the actual value like we just did on the front. So I'll give you a second to check. If you get example 1, you can go ahead and try example 2 as well. So we're trying example 1 and example 2 using the two methods we just went over on the front page. All right, let's see what we came up with here. So for example 1, method 1, it says the first method we should use is our synthetic division. So what are we dividing by if our factor is x plus 2? What are we going to put in that box? Right. So we change the sign, and then we've got all of our coefficients. So we got 4, -1, 2, and -5, right? All right, so we bring that first term down, we multiply, we add. We've got 20, and then we got 40. So in this particular case, we got a remainder. So is it a factor? No. So no factor or not a factor. Okay. We also can find this by using method 2, which is that remainder and factor theorem, where I can just take the factor, substitute it into the equation, and see what happens. So if I did that, we're plugging in, remember, -2. So I'd have 4 times -2 cubed minus -2 squared plus 2 times -2 minus 5, right? Okay, so order of operations would tell me I should simplify what first? The exponents. Okay, so we've got one here. What is -2 to the third power? Right. So we'll have 4 times -8. And then we also have another one here. negative 2 squared becomes right. Okay. All right, so then now that we've taken care of the exponents, now we can multiply, right? So I've got 4 times negative 8, which is negative 32, minus 4, and then 2 times negative 2 would be negative 4, minus 5, right? And now I can go and subtract. But are we going to end up getting 0? No. So it does not equal 0. I believe we get what, negative 45? Yeah, so since we do not get 0, same thing, right? These two methods gave us the same outcome, okay? All right, so let's check example number 2. This time they tell us the factor is x minus 2. So when I do synthetic division, I'm going to actually put positive 2 in here, right? Okay, so we'll have 2, 5, negative 8, negative 17, and negative 6. So I'm going to bring down that first term. We multiply and add, multiply and add, multiply and add. And what do we get? We think it's a factor? Yes, yeah. So yes, this one is a factor because we got that remainder of 0, right? So x minus 2 is a factor. Okay, so let's make sure that the other method would work as well. So I would go back up here to my original function. I would have 2 times, remember this is the value I'm plugging in, 2 to the 4th plus 5 times 2 to the 3rd minus 8 times 2 squared minus 17 times 2 minus 6, right? Okay, so again, I would have to take care of the exponents first. What is 2 to the 4th power? 16. So I got 2 times 16. And what's 2 to the 3rd power? 8. So I'll have 5 times 8. And 2 squared, 4. All right, okay, so there's all of my exponents. Now I can go and multiply, right? So what is 2 times 16? 32. And 5 times 8? 40. And 8 times 4? And 17 times 2? 34. And then we have our minus 6, right? Okay, so what is 32 plus 40? 70, okay. So then I'll have 70 minus 32 minus 34 minus 6, right? Oh, 72, thank you. Okay, and what is 72 minus 32? 40. So I've got 40 minus 34. And what is 40 minus 34? 6. And what is 6 minus 6? 0. Okay? So because it did end up giving us 0, that means there was no remainder, right? So that's why both of these methods will work. Okay, so both of these gave us the same outcome. Okay, this tells us the factor is x minus 2, so that tells us that we actually have the coordinate point 2, 0 as a 0 or a root, right? Okay. All right. Now, like we said on the front, if we are using that rule that says the degree matches the number of zeros in our equation, some of them might be imaginary numbers, right? We said we could have some imaginary roots. These are also called complex numbers. Our imaginary numbers can be referred to as complex numbers. And these usually come about in pairs. So if you find one, you should have a second one. It says, let f of x be a polynomial that has some real coefficients. So the numbers that are the coefficients are real numbers, not complex numbers. And if you get a plus b times I as a 0, then you should also get its conjugate, a minus b times I, as a 0 as well. Okay? So it says, is x equals I a 0 for this function here? If so, what else must be a 0? Okay, well, x equals I. That means to go plug in I for x, right? Okay, so then that would be I to the 4th power minus 2 times I to the 3rd power minus 2 times I squared minus 2 times I minus 3. All right, and then I know in Algebra 2, you guys talked about what I is equivalent to. So remember, I is my imaginary number, and I can't take square roots of negatives, right? Okay, I means it's like a basic number. It hasn't been multiplied or divided by anything. So if you guys remember, you fill out kind of like a table in Algebra 2, but that I is equal to the square root of -1. And then from that, you're able to deduce a few more things. I squared. Well, if I square the square root of -1, the square and the square root just kind of cancel each other out, right? So I squared is -1. Okay, I cubed would be -1, right? Because it's got at least a square in it, times I, right? So really it would be -I. And I to the 4th would be I squared twice, right? And what's -1 squared? 1. And then you start to realize when you guys fill this out in Algebra 2 that the pattern just starts to repeat itself, right? Okay, so just a quick reminder of what those 4 terms are equivalent to, since that's what's in our equation here. Okay, so I to the 4th, well, apparently I can replace that with 1, right? Minus 2 times I cubed, and we said we could replace I cubed with -I. Minus 2 times I squared, which we said we can replace I squared with -1. Minus 2 times I minus 3. All right, so let's simplify what we've got here. So we've got 1 minus, we've got 2I times -I, which becomes positive 2I, right, when I multiply right here. Okay, and then when I multiply right here, -2 times -1 becomes positive 2, right? Minus 2I minus 3. And I could have gone and replaced the i's, but it just so happens this 2I and this -2I are going to cancel each other out, right? So not necessary. So I'm left with 1 plus 2, right, which would give me 3, minus 3. And what is 3 minus 3? 0. And we said if it gives us 0, it must be a factor, right? So we can say, therefore, x equals -I must also be a 0. Because remember we said up here that if one of them is a 0, so if our positive is, then its conjugate also is, right? So whichever one they gave us, we know that the opposite sign would be true as well. Okay, so if one of them works, then the other. All right. So for our complex numbers, if you've got one of them that works, then we also should have the conjugate. All right, we also have a test we can run in case they don't give you some factor to start with. They don't say, okay, try this factor. Well, you don't want to just start having to guess at what potential numbers could be a factor, right? So we have what's called the rational zero test. And it says for any polynomial, and they use this expression for our polynomial because they're saying that the coefficient could be any number and the degree could be any exponent, right? And it's going to usually, in standard form, start with the biggest exponent, and then the next exponent's one smaller and one smaller and one smaller, right? All the way down to having no exponent, right? Okay, we are going to call the first term of our equation, so the highest degree, we'll call it Q. And then our lowest, all the way at the end, whatever it happens to be, we'll refer to as P. Okay, and it says for any polynomial where it's in standard form, like this equation, let P be all the factors of this last term, right? And Q be all the factors of the first term. Okay, and this is going to help us come up with all the possible rational roots for this polynomial. Okay, so it says we can make a list by taking all the factors of P, dividing it by all the factors of Q, and this will give us a list of all the rational roots. Now remember, rational numbers are things that can be written as fractions, right? So irrational numbers are things like pi, decimals that go on forever. So we're not talking about those, just any rational numbers. This should help us come up with it, okay? So it says first we need to list out all the possible rational roots. Well, remember, we said the highest degree, which if it's in standard form, should be the first term written. And we're going to call it Q. And then the last term should have no exponent with it. We'll call it P. And we're just going to list out its potential factors. Basically, what are numbers that multiply to get us that term, okay? So remember, we're going to put P in the numerator of the fraction. So I'll write those first. Okay, so P, I'm looking at this value of 7 right here. Well, what are the only things that multiply to give me 7? 7. Right. And it could be a positive 1 times a positive 7 or a negative 1 times a negative 7, right? Okay, so the only factors here are positive and negative 1 and positive and negative 7, right? Okay, now we're going to do the same thing for Q. Okay, well, Q's coefficient is the number 2. Okay, and what's the only thing that multiplies to give me 2? 2 and 1. Again, could be 2 positives, could be 2 negatives, right? Okay, so positive and negative 1, positive and negative 2. All right, and then remember, they said to come up with all combinations, you divide P by Q, all right? Okay, so we will just make all the possible combinations we can. So I'm going to start with P. The first value we picked was positive or negative 1, right? And the first value for Q was also positive and negative 1. Well, if I divide 1 by 1, it's just 1. So my first combination is plus minus 1, right? Because 1 divided by 1 is 1. We wouldn't leave it as a fraction. Okay? All right. Now I'm going to keep that same term for P, but what was the only other option for Q? 2. Okay? All right. So 1 divided by 2 is going to stay 1 over 2, right? So this would be plus or minus 1 over 2. Depending on the combination, right? If you did 2 negatives, it becomes positive. You do a positive negative, it could be negative fraction, right? Okay? All right. Then I'm going to try out any other combinations. Well, the only other term I had for P was 7. So let's say we put 7 over 1 for Q. Well, 7 over 1 simplifies to just, so it could be plus or minus 7. All right, and then I could also make the combination of the 7 for P and the 2 for Q, which would just be 7 over 2, right? Okay, so it says all of these are possible rational roots, okay? So that definitely narrows it down, so we're not just taking a stab in the dark to pick some numbers, right? It says determine at least one from this list that is actually a 0. Well, that means we only have to try these 4 values and see which one might work, okay? So maybe we start with our first term, that plus minus 1, okay? So let's try doing synthetic division with a 1, and we'll see if we think it's a factor or not. Okay, so I'm going to have my coefficients of 2, 17, 22, and 7. So I bring down that first term. I multiply. I add. And what do you guys think? Is it a factor?
No.
No, because we got a remainder, right? Okay, so positive 1 was not a factor. Let's try negative 1. So we got 2, 17, 22, and 7. This time we're going to divide using a negative 1. All right, what do you guys think? Is negative 1 a factor? Okay, perfect. So then we would say x plus 1 is a factor, right? If we take that, put it into a factor, it changes the sign. Okay, so that's a factor, all right? Meaning that this did simplify down to 2x squared plus 15x plus 7, okay? And then it says in the section below that we need to use that one root that we came up with up here, which was x plus 1, and see if we can complete the factorization. Can we factor it all the way? Well, we just said this is what it became, right? 2x squared plus 15x plus 7 is what we got when we divided. What do you guys think? Can I factor that? What would that factor into? Nice. Okay, so the complete factorized form would include the 0 that we found up here, the x plus 1, as well as the factors that we just came up with, 2x plus 1 and x plus 7. All right, so what do you guys think? Where would we end up having zeros if I were to go and plot these on the graph?
-1, -7, and -1.
Good. All right. Okay, so let's see. -1, 2, 3, 4. Oops, I should have done those closer together. 1, 2, 3, 4, 6, 7. Okay. So I got 1 here, I got -1, and then 1/2 right here. Okay. All right, so it asks what the leading term of this equation was. Well, I need to go back to looking at it in standard form, which they wrote for us up here, right? What was the leading term of this polynomial? 2x cubed, okay. So that 2x cubed tells us to expect what for end behavior? Okay, and then they also ask, at these zeros, are we just going to be going through the line? Are we going to bounce on the line? Do we have any wiggle? Just through on all of them. Okay, all right, so then we should be able to draw a sketch. And it's going to look something like this, right? So let's do one more of those. So we have to start out with coming up with potential factors, right? And we do that by looking at Q and P. So first, I'm going to worry about all of my factors of P. Oops. So P here Yeah, P is our 8, or in this case, I guess, -8. And what are some things that would multiply to give us 8 or -8? 8 and 1, okay. 4 and 2, okay. So we're going to just put plus minus on all of them because we don't know, right? We don't know which one would be positive and which one would be negative. So plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8 is all the ones you listed for me, right? Okay? Okay, let's do the same thing for Q. So looking at my term Q, it's the coefficient 2. What are the only things that multiply to give us 2? Right. So positive and -1, positive and -2. All right, and then remember, we write these as P over Q. So we're going to list out our combinations. So first combination would be plus minus 1 over plus minus 1, which really is just 1, right? Okay. I also could do, for P, that plus minus 1 over, what's the other option for Q? So plus or minus 1 over 2. All right. That wears out all the combinations for using the plus minus 1 for P. My next option for P is the plus minus 2. So I could do plus minus 2 over 1. 2 over 1 is really just 2. So I'd do plus minus 2. All right, and then I could do plus minus 2 over plus minus 2, but 2 over 2 simplifies to which we already included, right? So that's not a new combination, okay? So now we've used that for P. Let's try the 4. So 4 over 1 would just be 4, right? So we'll do plus minus 4. I could also do the 4 over 2, but 4 over 2 simplifies to which we already have that in our list, right? So we don't need that, okay? And then my last option would be to use 8 for P. So I could do the 8 over 1, which would just be 8, right? And I could do 8 over 2, but 8 divided by 2 is which we already included. So these are all of our possible combinations, right? This time it says determine at least 2 from the list that are actually zeros, okay? And you don't have to start with the first one and work your way down. Maybe you say, oh, well, last time positive 1 didn't work, but negative 1 worked, so I want to start with negative 1. We could most certainly do that. Or maybe you say, oh, I think that the 1s aren't going to work. I want to start with 2. It doesn't matter where you start, whatever you think might work. So I'm going to try the 2. So then my coefficients are 2, -5, 3, 2, -8. All right, and sure enough, 2 does work. And just to save you some time, I'm going to go ahead and give you another one that will work. -1 does work. I don't know if anybody's tried that one yet. But I'm just going to, instead of starting back with the original, guys, I'm going to use these coefficients that I just came up with. So it goes ahead and keeps factoring for us because you know what's going to happen next is they ask us to factor the whole thing. So 2, -1, 1, and 4. And sure enough, same outcome, right? All right, so these would be the factors x minus 2 from that first one, right? And x plus 1 from that second one. Okay, and then that leaves us with 2x squared minus 3x plus 4, right? Can we factor that any further? When it asks for the complete factorization on that next line, does 2x squared minus 3x plus 4 factor? Well, we know here it has to be 2x and x, right? And then the only possible combinations that multiply to give me 4 would be 2 and 2 and 1 and 4. But is there any way we're going to end up getting that negative 3 in the middle? Okay, so it doesn't factor any further. So as far as it factors, we would only be able to include the x minus 2, the x plus 1, and the 2x squared minus 3x plus 4 would be how we would have to write the factorization there. Okay, so it didn't factor. So this time, the only places we were able to come up with actual zeros were going to be for these two pieces, right? We would have zeros at 2 and negative 1. Neither one of them have an exponent, so we know they should just go through, right? Okay, and looking back at the original, what was our leading term? Right? And we should expect for our end behavior, up, up. Okay. All right, tomorrow we're going to talk about what this graph should look like because of this piece right here. All right?